All right, let's look at problem number 21 on this exam 1 sample problems. We want to find the distance from the given point to the given plane. So we're going to use this little formula right here. There's two ways you can kind of do it. The bottom formula works well if it's between two planes, as I showed in my notes. But we have to find a point, any point on the plane, so that we can create this vector PQ, which is from this point S to that point on the plane. And then we'll dot that with the normal vector of the plane. So it's real easy to find any point in the plane. Basically, you're just looking for any three values for X, Y, and Z that will make the equation true. So anything that makes it true would be on the plane. All right, so I find the easiest way to do this is just let a couple of the numbers be 0 and solve for the third. So if I put in 0 for X, 0 for Y, Z would be 7. So 0, 0, 7 is a point on that plane. But this works no matter for any point on the plane will work. For example, 1, 1, 3. That would give me 7 if I put in 1, 1, 3. Guarantee if you took 1, 1, 3, did the same process, you'll get the same answer. So it really doesn't matter. Also, the P to Q order on this makes no difference. So it doesn't matter which point you subtract from the first point. So it looks like I called basically the 007 as P, and then the point S here would technically be the point Q in the problem. So 5 minus 0 gives you 5, 2 minus 0 gives you 2, and 3 minus 7 gives you negative 4. So that would be my PQ vector. And then, of course, the normal vector for the plane will be the coefficient. So it'll be 2, 2, 1. I didn't write that down, but now you're hearing me say it. So that's the normal vector. So if I dot 5, 2, negative 4 with 2, 2, 1. So I get 5 times 2 is 10. 2 times 2 is 4. Negative 4 times 1 is negative 4. You add those up, you're going to get 10. And then the formula has the absolute value in the numerator to protect the fact that the answer has to be positive. We don't need the absolute value in the denominator because magnitude is always going to be positive. Because it's a distance, so it's got to be a positive value, or technically 0. It could be if it's on the plane, the answer would be 0. But that's not going to be a question that would be asked on an exam. So then the magnitude of a 221, so I didn't show the work here, but 221 would be square 2, 4, 4, 1. Add those up, you'll get 9, and the square root of 9 is 3. So that's where the 3 came from. And then we have 10 over 3 is the distance from that point to the plane. All right, pretty straightforward formula. Same thing with this one, distance to the point on the line. This time, though, involves a cross product. So the point Q that they give in the formula would be the S right here. And we have to find any point on the line here, which is super easy. Just pick any value for T. I just chose 0, but you can choose anything you want. So if you put 0 in there for T, you're going to come up with this point, 7, negative 6, negative 1. So I have to create a vector PQ, or it could be QP. The order doesn't matter. And I just wrote from P to S, but S to P would have been okay. So there's that point that we found on the line. And then let's see, the given point. Oh, went too far. The given point S is negative 7, negative 10, negative 7. So we have to find the vector between those two. So negative 7 minus 7 is negative 14. Negative 10 times negative 6 is negative 4. Negative 7 minus negative 1 would be negative 6. Now, I just made a note here that just to do because this is fine. Like I said, the direction of the vector makes no difference. And had I chose the other order, I would have got this answer. So, and I mentioned I just did this for the cross product ease. I just went with the positive of this, 14, 4, and 6. But you don't have to worry about doing that if you don't want to. So I'm going to take 14, 4, 6, cross it with 2, 1, 2. I don't have the cross product here right here, but I have it, cut out in earlier problems, and obviously you have it available. I showed the cross product one time in the first set of problems on this review. I haven't shown it since, but just follow the cross product formula. There it's written out. And I would have, doing this cross product, I would have considered pulling out a 2 out of this thing. And then you end up, which just would have been the same thing. You could have simplified the radical at the end. That means there would have been a factor of 4 out of there. But it's going to be 2 square root of 74. And then the u, the vector, direction vector for the line, 2t, 1t, 2t. So it's 2, 1, 2. The magnitude of that is going to be 3. It's going to be 4 plus 1 plus 4. Square root of 9 is 3. So the distance from the point to that line will be 2 square root of 74 divided by 3. Find the angle between the planes, which is, it's using the angle between two vectors, because to find the angle between two planes is all we have to do is find the angle between their normal vectors. Because, the normal vectors are just 90 degrees away from the plane. So if both normal vectors are exactly 90 degrees away from each other, from the planes, that means those two vectors, the angle between those vectors would be exactly the same as the angle between the planes. So that's what's going on here. And we just take the two normal vectors, which would be 8, 3, 4 for the first one, 2, 9, 8 for the second one. And we dot product. Now, unlike the other angle between two vectors we saw before, where it was u dot v, that one didn't have an absolute value in the numerator, and why this one does is because the answers must be between 0 and 90 degrees. So it's going to keep cosine positive, which makes it in the first quadrant. For between two vectors, it was okay for it to be anywhere between 0 and 180. So that's why you could have negative cosine values in quadrant 2. But no, this is strictly quadrant 1. We're looking for the shortest angle between two planes. So we dot those two vectors, n1, n2, and I got 75 when I dotted them. Then we need both of their magnitudes. And let's see what we got here. So it's going to be cosine inverse. Both magnitudes of n1 will be square root of 89. n2 will be square root of 149. So then theta is going to equal cosine inverse of 75 over the two magnitudes multiplied together. And I didn't have the calculator screenshot here, but I'll just do it real quick so we can see it. I want to make sure I'm in degree mode. I am. So I want to go cosine inverse 75 divided by, I want to put parentheses here. And let me see what those numbers were again. 89 and 149. So second square root. Actually, you can multiply the two numbers under the radical if you want to also. That would work. That would be mathematically correct. I already forgot again. Let's see. 149, yeah. So I'm going to move this over. I'm going to close that parentheses off and then close the parentheses off for the whole thing. So you see that way the two radicals stay together in that denominator. And let's see what we get. So whatever you have to round it to, 1 or 2 decimal places. So it's on a test, it would either be 49.4 Or maybe the whole number angle, who knows. But 49.4 or 49.36, yeah, it's not going to be with a bunch of crazy answers there. I mean, with a bunch of decimal places. I have two, okay, so. Oh, and also I just showed what that was in radians, just in case. I mentioned that before, and the angle between two vectors is, generally it's going to be degrees, but I just want to mention also, just put the calculator in radian mode then if it needs to be radians. Just read the instructions. So there we go, takes care of that. Domain. Now we're getting to the chapter of vector valued functions. The domain of a vector valued function is the values for t that can be used in all components. So basically it's got to be, if it's true for one, it's got to be true for all. So what I like to do is just identify the individual domains, and you don't have to really worry about anything that's all real numbers, because you can just kind of throw, they're all real numbers, and the answer is all real numbers. But even one part of it being all real numbers is not important, because we're looking for restrictions. That's the key, is what would satisfy all this one. So for the first one, for the I component, t could technically be anything other than 8. So we know that 8's eliminated. But now we go to the next one. T can only be 7 or less. I should have graphed these. Yeah, I mentioned that right here. I did that in the notes by graphing them. 7 less than or equal to 7. And the natural log, you can only take log of a positive value. So this one would have to be... well, actually, with the absolute value, everything except 8 is going to be positive. So the only thing you would throw out there is 8. Now, that's a weird coincidence that the first and the third had the exact same restriction. Well, that's fine that t can't equal 8, because it's not really less than or equal to 7 kind of ruins 8 anyway. It's not part of the domain. So less than or equal to 7 is the common domain for all three of those, so therefore it's the overall domain of the vector valued function. So just do each domain. You can even write them like I did in my notes. Write them like 3 separate number lines, and just kind of look at them and see where they share common ground. All right. So there's domain. Limit. You can use any method you want. Limits. These just happen to work all by L'Hopital's rule. Sometimes you might be able just to plug the number in and get an answer, but what you have to realize is that anytime that you get 0 over 0, the limit may exist at that component. It's when if you get something like 5 over 0, then you have do not exist. We're not worried about infinity or anything like that. For this, we would just say does not exist. So if any one component fails, the whole thing fails. So it's important to remember that the limit of a vector valued function is a vector. So you're finding the 3 individual pieces that will compose an I, J, K vector. They're not going to be, you don't find the 3 values and then like add or subtract them together or anything like that. There's 3 separate answers, 3 separate numbers that are put into one vector answer. Okay. These all happen to work by L'Hopital's rule, but just to give you a brief review, this first one could have been done by using Cal 1 techniques, where you factor the denominator, cancel the t minus 1s. That would have worked. But L'Hopital's rule was easy enough, because it was a 0 over 0. When you put in 1, you get 0 over 0. So take the derivative, and if t minus 1 is 1, t squared minus 1 is 2t. Now you can plug the 1 in again, you'll get 1/2 for that component. The next one, I just took the negative here, the negative in front of the j, and put it essentially up with the numerator. As long as you take the negative of the whole thing, but you do need to include the negative. And this one is also 0 over 0 when you put 1 in there, so L'Hopital's rule applies. So now I distributed the negative after I took the derivative. So it's negative 2t minus 2. And at the bottom, t minus 1 would be 1. I can reinsert the 1, and now I get negative 4. Now the next one, natural log of t over t minus 1. You put in 1, you'll get 0 over 0. So the derivative of natural log of t will be 1 over t. Derivative of t minus 1 will be 1. And put in 1 again, and you'll get 1. So that's the vector 1/2, -4, and 1. Sometimes I've seen, exam generators, and even the one that I use might try to trick you, and then one of the answers might be a single number answer with all three of those numbers added together. Never pick that answer. It's got to be a vector answer. Same thing for derivatives also too. The derivative of a vector valued function, whether it's just in terms of t or at a point, it's a vector answer. It is not a number. It's not like what you're used to thinking too in, single variable calculus where you say, find the rate of change at x equals 2. You find the derivative, put the number in, and the answer will be a single number. Not here. These are vectors. All right, we want r prime and r double prime. I like this one because, got to remember cosine and sine. Then also you have to pay attention to the chain rule. Very, very, very important. All right, the derivative for this one of cosine is negative sine. Now, where the 4 is coming from is the 2 coming down and the derivative of the argument of the trig function. So the derivative of 2t is 2. That goes with the other 2 to make it 4. And it's negative because the derivative is negative. So it's -4. Yeah, a lot of people forget that. They forget to take the chain rule on those derivatives. Very important. And then for this one, same thing here. Now there's a negative here. Now this negative is not from the derivative. This negative is coming from the subtraction. Because the derivative of positive sine is positive cosine. Or you can look at it then as the derivative of negative sine is negative cosine. So the derivative of 2t is 2 again. So it brings out a 2. So it's -4 cos of 2t. Then you just put in the pi over 3, which you can just get those off the unit circle. That's easy enough. Sine of 2 pi over 3, quadrant 2, that's going to be square root of 3 over 2. And then it'll be -1/2 for cosine. And then you get -2 root 3, comma 2. Second derivative. Now sine to cosine stays the same, sine-wise, S-I-G-N-wise. The negative, because there's a negative there, so negative again, brings out another 2 from the chain rule to make it -8. Now here, the derivative of cosine is actually a negative sign, but the negative that's already in front of it will turn that negative into positive. All right, so we have 8 sine of 2t here because another 2 will come out from the chain rule. Put in pi over 3, same idea. You'll get 4, and then comma 4 root 3 will be that vector. Okay. Now here's an integral that just has one component. The next one will have more than one component. So technically it is a vector. Now I did just list it as, I put it in standard unit vector form by just putting j there, which is fine. But if it was written in component form, it would be 0, comma, the number in parentheses, comma 0. Because the I is 0 and the k is 0 because there's nothing there. Okay, it's a pretty easy integral. It looks like it might be complicated, but it's just u substitution. Because it works out great because the t squared, the derivative of t squared will give you the t that you need out in front. So we're in good shape there. So a little u substitution, so let u be t squared, du will be 2t dt. I always like changing my limits of integration. You may not do it this way from how you learned in calculus. That's okay, just be careful what you're doing. But I like to do this because once I change this over to u, including the limits of integration, I never have to go back to the original variable again. So if I put in the square root of pi over 2 into t squared, I square that, I'll get pi over 4. I put in 0, I'll get 0. So now I have new limits of integration, 0 to pi over 4, and just sine of u du. And technically it is a vector component, so the j is there. Oh, and the 1/2 comes from right here, obviously. If the du is 2t, we have to divide both sides by 2. That means t dt is 1/2 du. So I just took the 1/2 to the outside. So we just got through taking derivatives of sine and cosine, but be careful with antiderivatives, going backwards. The antiderivative of sine is negative cosine. Not the derivative, the antiderivative. And then just put in pi over 4, put in 0. Cosine of pi over 4 is root 2 over 2. Cosine of 0 is 1. And I just got, I mean, this answer's fine, but I just got a common denominator for the 1 and made it 2 over 2, and then multiplied 2 times 2 and got 4. I just kind of cleaned it up a little bit. I didn't really do anything, mathematically creative other than just kind of tidy it up a little bit. So that's it. That's just a single component integral there. So let's see what the next one. So now the next one's got 3 components, 3 separate integrals. First one's going to be a u substitution. The third one will be a u substitution. The middle one's simple because it's just 3t squared. So let's say I just brought the square root of 1 plus t up to the top to make it 1 plus t to the negative 1/2. So u equals 1 plus t, makes du equal dt, so nothing to adjust. It looks like this one I did not change the limits of integration. So, yeah, well, I did for the last one, but I didn't for this one. That's weird. But anyway, I'll tell you what I would have done. I don't know why I didn't for that one. But it doesn't matter, but I guess I should stick with my consistent way to do it, but I won't worry about that. So now we just take the antiderivative. So in other words, I wrote it as an indefinite integral because I changed it back to t. U to the negative 1/2 du would have been 2u to the 1/2. So let me tell you what I would have done otherwise. I would have put 3 into 1 plus t and got 4. I would have put 0 and got 1. So then I would evaluate, of course, the 2 comes in. So it would have been 8u to the 1/2, and I would have put 4 on top and 1 on top, and then plugged it in. That would have been the answer. I can already see that's going to be right. So I decided to go back to t instead, which I normally don't do, which is strange, but that's all right. Got it right, though. So I replaced the 1 plus t back in and put 3 and 0 in there. Sometimes I see people mess this up, is that they'll change the limits of integration and then they'll go back to their original variable. That's no good. Then you've kind of messed it up that way too. So anyway, put in 3, you get 4 to the 1/2, square root of 4 is 2, square root of 1 is 1. So you get 8 times 1i, so that the first component is going to be 8i. Middle one's real easy. Antiderivative of negative 3t squared is negative t cubed. Put in 3, put in 0, negative 27. J. The k component is going to be u substitution. This one I did change the limits of integration. U equals 1 plus t squared. Du would be 2 dt, which will bring out a 1/2 to the outside. U of 3, 1 plus 3 squared is 10. 1 plus 0 squared is 1. So I have a 10 that just comes from the original problem, a 1/2 that comes from the du, and then I'm going from 1 to 10, u to the negative 2 du, just put the k there, and the antiderivative of u to the negative 2, if you just do the power rule, you're going to get u to the negative 1 over negative 1. Well, 10 times 1/2 will be 5, and then the dividing by the negative 1 just makes that a negative 5. And then you just plug that in. U to the negative 1 is just 1 over u. So actually you would get negative 5 times 1 over 10 minus 1. So it's basically 1 over 10 minus 10 over 10, negative 5 over 10. Negative 9 over 10, excuse me. Negative 9 over 10 times negative 5 would be 45 over 10. And then I just reduced it, just because that's probably the way the final answer would look. But maybe not. Okay, so I just kind of skipped the arithmetic there, which you can just do that in a calculator if you want to. That's fine. So there's your vector, your integral vector there. So excellent. So we're solving an initial value problem where essentially it's giving us the derivative and we have to integrate back to get the original vector valued function, but we're also solving for c. Now, because if you just integrate a vector valued function with no numbers in it, you still have a constant there. Now, of course, that constant is technically a vector because you can't add, you can't have plus c a number, because if this is a vector and a number do not add up. You can multiply a vector by a scalar, but for example, you couldn't take the vector 1, 2, 3 and add it to 6. That makes no sense in vector algebra. So the c is also a vector. Well, we're going to solve for that vector c because we know this information right up here. But first things first, we have to do the integral. Not too difficult. This one, 27t cubed, you just use the basic power rule. You get 27t squared, and you'll get 9t cubed. The antiderivative of negative 2 will be negative 2t. And the antiderivative of negative 1 in the middle, negative 1j, would be negative tj. And then this one, maybe I could have written it out as u substitution just to be a little more formal. But I think I'm confident that you can come up with that. But basically it's t1 plus t to the 1/2. You could actually use the power rule here. The derivative of the inside is 1, so the du doesn't have to be adjusted for. And then using the power rule, you'll end up with this result. 2 times 1 plus t to the positive 1/2 power. Now I'm going to plug 0 in there because I want to see what that equals at 0. So let's see what happens here. I'm going to plug in 0 into this, and I'm going to set it equal to what r of 0 is supposed to be. So the left side here is what r of 0 is supposed to equal. Then I'll put 0 into r of t. That way r of 0 is on the right side, and then the actual value, the r of 0 from the integral, is on the right side. So if I put in 0 here, I'll get 0 for I, 0 for j, but I'll get 2k on the left side plus c. So now we have the negative 7i plus 3j plus 8k equals 2k plus c, and therefore we can make the c fit be what we need it to be, and there's only one component on the right side, so that's easy to move. So you just subtract 2k on both sides, and then you would have the c must equal negative 7i plus 3j plus 6k. Now, technically, it wouldn't be mathematically wrong then if you said the final answer was this part, blah, blah, blah through k, and then plus that vector we just got for c at the end. But it's generally not written where you have like a bunch of separate i's, j's, and k's written all over the place. It's better to group them. It's better form to group them as 1i, 1j, and 1k. So we already have a 9t cubed minus a 2t there, and then we just put in the negative 7. That way we essentially grouped all the I values together. Same thing, this one I have a negative t already here. Now I have a plus 3. So it'll be negative t plus 3 and then j. And then for the last one, I have the 2t. I don't know why I changed it back to radical. It doesn't matter whether it's a radical or not. But anyway, that part's here. And then I have a 6k. So I would put 2 square root of 1 plus t plus 6 will be my k component. So that final answer satisfies two conditions. Its derivative will equal what dr dt is given to you in the problem. And then when you put 0 in for t into that answer right there at the bottom, you'll get this result right here. So it serves two purposes. And that's how we do an initial value problem. Number 30. All right, velocity and acceleration. Velocity's first derivative. Acceleration's second derivative. They didn't give us a value. Sometimes you might be given a value t, obviously. They'll say find it. So you would just plug the t in afterwards. And I find this kind of weird how this problem's written. Usually, usually you don't, it doesn't hurt anything, but the I and the J would be at the end of the function, kind of like the K is. It's weird putting it there, but it's no harm mathematically speaking. But now this one does not have chain rule issues because it's cos of t and sine of t. It's not like cos of 3t or sine of 4t, so it has no issues there. But you just have to know the derivative of cosine is negative sine. So the I component would be negative 2 sine of t. The derivative of 2 sine of t will be 2 cos of t. And the derivative of tk will be 1. And then to get the acceleration, that will be the second derivative. So the derivative of negative 2 sine t will be negative 2 cos t. Then the derivative of 2 cos t will be negative 2 sine t. And then the derivative of 1, which is the derivative of t, is 1. Then that derivative will be 0. All right, let's take a look at problem number 31. The velocity and speed at t equals pi over 4 for the given position function. And I put the answer to the speed over here to the right because it won't be on the answer key to the original because I just added that into the question. All right, so let's see what we got here. We've got to take the velocity, of course, will just be the derivative of the position function. And let's see what we have here. Now, got a little bit of a chain rule for this first one, 5 sec squared. So if you think of u being secant, you're just taking the derivative of u squared, 5u squared specifically, but let's forget about the 5 for a minute, which would be 2u du dt. So the 2 is going to multiply by that 5 to give you 10, and then the u will be secant, and then du right here in parentheses is the derivative of the secant, which is sec 10. Now, if I was just going to not be plugging a number in for this, just getting the velocity vector function, I would probably combine the two secants together and call it secant squared. But we're going to be plugging pi over 4 in, so it doesn't really matter too much. We can leave it like that. And then, of course, the derivative of tangent is secant squared. And then the derivative of 10t squared would be 20t. So we put in pi over 4. Secant at pi over 4 is 1 over cosine, so it's going to be the square root of 2. So you basically have, and tan of pi over 4 is 1, so you have 10 times the square root of 2 times the square root of 2 times 1, which will make 20. And then here you have the square root of 2 squared, which will be 2. That'll make that one 8. And then you just put 1 in there. Pi over 4, excuse me. Put in pi over 4, makes that 5 pi. And there's your velocity and vector. Now, speed is not a vector. Speed is a scalar quantity, but it's the magnitude of the vector. So we take the magnitude of this answer right here. So it would be 20 squared plus negative 8 squared plus 5 pi squared. And that's just going to equal the square root of 464 plus 25 pi squared. And obviously you could get a decimal if that's what the answer wants, but it's, most likely probably just will look like that. That takes care of that one. Let's take a look at number 32. Acceleration is the second derivative. We want to find that at t equals 0. So the first derivative, velocity, is t squared will be 2t. 6t cubed minus 7 will be 18t squared. And then the 1/2, you'll bring the 1/2 down. You'll subtract 1, make it negative 1/2. Chain rule says we need the derivative of the inside, which is negative 3. And then the next derivative, 2t will be 2. Those are easy. 18t squared will be 36t. Now, what's happening here is, so you're going to bring down a negative 1/2 times that positive 1/2, which will make it negative 1/4. But you'll take the derivative of the inside again, so it's going to be another negative 3. So you have negative 3 times that negative 3 makes 9. So 9 times what would have been a negative 1/4 there makes it negative 9/4. And then you put in 0, 0, 2, that'll be 0. You can do that in a calculator, but it is correct. Because 9 to the negative 3/2 is 1 over 9 to the 3/2, which is 1 over 27. So if you take negative 9 over 4 times 1 over 27, that reduces to negative 1 over 12. And then there's your acceleration vector at t equals 0. Okay, these projectile problems. Parametric form. You got a couple different functions to work with. And these three I have right here are generally one of those kind of threes, what I put on the test. I'm not going to get too creative here. Although I'm sure they could get more creative. But I'm not trying to turn this into a physics class. So let's see what we got here. Launching a projectile at 26 degrees, initial velocity of 48 meters per second, which really is velocity. I guess speed's probably the wrong word to use there. But that's okay. We're not worried about the semantics on this one. Because the difference, like going back to that last problem, speed is a scalar value. Velocity and acceleration vectors, meaning they have direction. Speed has no concept of direction. It's just a number. So let's see what we got here. Well, how far does it hit the ground away from the projectile? Okay, we can do that. So we want to know, obviously this one's starting on the ground, so we want to know when it gets back to the ground again. So we need to, when it's on the ground, we know there's a height of 0, correct? So y, which represents the height, x represents the horizontal distance, the range. So let's see what we got here. So we're going to take the y equation, set it equal to 0. There's no initial height here, which is good because that would cause us, we'd have to use quadratic formula if there was a number there. Just a little more tedious. And we're in meters, metric, so 48 V0 sine theta would be 48 times 26, sine of 26, times t, minus 1/2 gt squared, so 9.8 or 9.81. This is good, close enough. So half of that, so it's half of that squared. Negative 1/2 times 9.8 t squared, so it's negative 4.9 t squared. So now we're trying to solve for t. So I factored out a t, which we don't want see, one of the solutions is definitely t equals 0, but that's the starting point. So we need to solve for the second t here. So just solve what's in the parentheses equal to 0. That's easy enough. Just move the t over, divide by 4.9. So you get 48 sine of 26. Make sure, as I mentioned here, that we're in degree mode. Divided by 4.9 is roughly 4.294 seconds. So about 4.3 seconds for it to hit the ground. So how far did it go? That means we want to know the x component. So we want to know what the value of x of t is when t equals that number 4.294. So we come up here to the V0 cos theta t. So put in 48 cos of 26 degrees, and the time is 4.294 seconds. And you get approximately 185.3 meters. So it was in the air about 4.3 seconds and went close to 180, right at 185 meters. There we go. That one wasn't too bad. Number 34. Projectile fired at initial speed of 528 meters per second. Angle of 45 degrees. What's the greatest height reached by the projectile? And, well, before we get the height, we need to know how long, what time it takes where it'll read the maximum height. Now, the maximum height is going to occur where the derivative of the y component is going to be 0, because that's where you're going to have the horizontal tangent line, you may recall back from Cal 1. So we want to find where the derivative equals 0, and that's where the downward parabola will reach its highest point. So we have the y will be, there's h is 0, initial height 0, so we have v0 sine theta t, so it's 528 sine of 45t minus then 1/2 of 9.8 times t squared, so it's 4.9 t squared. We take the derivative of that. Now, one thing you want to watch for here, sometimes people will ask me about this, is that you're not taking the derivative. It's not sine of 45t. In other words, there's not a chain rule issue here. It's just the derivative of sine of 45 all times t. So basically the derivative of, so it's just 528 sine 45, because the derivative of t will be 1. So sine of 45 will be root 2 over 2, and this component will have a derivative of negative 9.8t. And then we'll set that equal to 0. And it's pretty easy to solve from there once you set that equal to 0. Easy algebra to solve for t. We get 38.1 seconds. Now to find, okay, what is that greatest height or maximum height? We take that 38.1 and then we plug it into the y equation. The original before you take the derivative. We plug it in there. Now because all this kind of didn't all display properly on one line, I went ahead and did it in two pieces there. So I typed in the part before the minus, hit enter, and then did the part after the minus just so we'd see everything. So it's 528 sine of 45 times the t, which is 38.1 that we just found, and then hit enter, minus 4.9 times the time, 38.1 squared, and I got 7,111, and then 0.8. I believe they wanted rounded to a tenth, so it'd be 7,111.8. Number 35. We're firing a tennis ball at an angle of 58 degrees. Ball lands 11 meters away. What was the ball's initial speed? All right, so we know it's traveling a horizontal distance of 11 meters, so that's going to be our x. So what we can do is plug that in for x, and we have 11 equals v0 that we don't know. That's what we're solving for. And we also don't know the time yet. Cosine of 58 degrees times t. So you see the problem is we have one equation but two variables. So what we're going to have to do is take the y equation and also get it in terms of t and v0. And then we would have two equations, two unknowns, and we can solve it by substitution. So what I've done here is taken this equation and I solved it for t in terms of v0. And the reason for that is that I want v0 to be the variable that we'll be solving for. So that way we'll be eliminating the t, in other words. It'll just be v0 is the only variable. So t0 equals 11 divided by t equals 11 divided by v0 cosine of 58. Now when it hits the ground, we know that y is going to be 0. We know that. And so it'll be 0. And I went ahead and factored out a t already. So there would have been a t, there would have been a t squared there. So a t is already factored out. And because we're going to eliminate the t equals 0 because we don't care about the starting point. So 0 basically equals v0 sine of 58 minus 4.9t. Then we're going to plug in for t what we just got up here. So you move this negative 4.9t over to the other side. It becomes positive. Replace t with 11 over v0 cos 58 equals v0 sine of 58. And let's just kind of multiply both sides by the denominator, or you can cross multiply. Some, instructors don't like to use the phrase cross multiply, but I don't mind. But what I did here is I multiplied, I essentially brought the, v0 up, but then I brought the sign down, which is the same thing. So the v0 came up with the other v0, and I have v0 squared, and I have 11 times 4.9, and now basically divided both sides by sine of 58. So sine and cosine are down there together, but you see that's v0 squared, no problem. All we have to do, in other words, make sure you're in degree mode, of course. You just have to square root all this quantity on the right side of the equation. So just make sure you square root it. and that will give you your initial speed. So it's the square root of all this mess here, and I got roughly about 10.95 meters per second would have been the initial speed. Problem 36. So we have a position function, and it wants to know the curvature, and then the tangential and the normal components of acceleration also at the point 632. Now, most of these problems will usually it'll tell you like t equals something, t equals a number, but I like this because it kind of gives a little different twist to this, and this was in my notes with one of the examples, at least I know one of them, but probably more. But they can either give you the t directly or give you a point, because if you have a point, you can then figure out what the t is going to be with no trouble. So you look at this and go, all right, so I need this position function to produce that point at a value for t. Very good. So if you have the first component is 6t, and then the first component here in the point is 6, that means t would have to be 1. Now, I would double check that and make sure that fits the other components, because sometimes you have to be careful that, let's say if that would have been 6t squared, because then that way -1 or +1 would have made it equal 6. So then you would have seen which number needed to work for all three of them. That's the key. So this one's obviously 1, so it's 6. Put in 1 to make sure. 3 times 1 squared is 3. 2 times 1 cubed is 2, so that t equals 1. So same thing as t equals 1. Here's the curvature formula that I like to use the best. The two derivatives are easy enough. 6t will be 6, 3t squared will be 6t, 2t cubed will be 6t squared. A second derivative will just be 0, 6, and then 12t. Now one thing I showed the cross product here. Now one thing I probably should have done, it's not mathematically wrong, so that's the good news. But I probably should have put the 1 in here and then just did the cross product. That's okay, but here's what happened. I did the cross product as is with the t's and came up with this. And then down here, I put the 1 was put in for the t. So all that would have happened is if I would have put in the 1 originally, I would have come straight down and got this 36, -72, 36. I think that would have been a little more efficient, but nothing bad. So I do regret that choice, but that's all right. But anyway, so at 1, it'll be this vector. So the formula says we need the magnitude of that cross product. So I'll pull out a 36, which you can do for magnitudes. You can pull out a constant multiple, and that would leave me 1, -2, and 1, which the magnitude of that will be square root of 6. And then you put in, it's r prime, the magnitude of r prime of 1 cubed. So you put in 1 will give me 666. And I pulled out a 6, basically. And it's going to give me 111, which will give me a magnitude of the square root of 3. So that's going to be 6 square root of 3 will be the magnitude, and then we cube it. And when you cube it, you're going to get 18. Well, I didn't show a step there. The 36 went away, but you basically have, 3 6s on the bottom because it's 6 cubes. So 6, 6, 6. 2 of those 6s take out that 36. And then now the square root of 3 cubed is 3 square root of 3. So you have a 6 left over and a 3 square root of 3. Multiply those together, you get 18 square root of 3. And if you rationalize the denominator, what happens is you're going to have multiply top and bottom by square root of 3. Or you can just divide that, because this one, since 3 goes into 6, that works. That will take care of the rationalizing. Is if you go square root of 6 divided by square root of 3 is square root of 2. So there's the curvature. Here are the, I use the a dot t. I like that one for the tangential component of acceleration. So it would be a1 and t1. Now, a1 will just be the acceleration vector at 1, which will be 0, 6, 12. And we know that r prime of 1 is 6, 6, 6. But remember, the unit tangent vector would be r prime divided by its magnitude. So it's it's related to the r prime vector, but it has to be a unit vector because it's called the unit tangent vector. So the magnitude then of there it is right there. We already have the magnitude. It's 6 square root of 3. So I have to take the 6,111 divided by 6 square root of 3. The 6's cancel. You do a dot product. You get 18 over square root of 3. Rationalize the denominators, and you'll get 6 square root of 3 for AT. Now, AN, either of these two formulas are fine. I went ahead and went with the one that was under the radical, but, you can use that first one. It's not too bad if you want to do a cross product. And actually, maybe I should have used that first one. I'm not that I wasted a lot of time on this one, but because we've already... Oh, yeah, because I didn't think about that, but because the curvature, if it wasn't for the curvature in this question, I would have for sure used the radical one on the right. I'm always so used to using that one, but I didn't catch this. Since we had to do R prime cross R double prime is V cross A. That's already done, so, oh well, my fault. But it's going to come out all right. That's the main thing. I'm not used to curvature being in the same problem with AT and AN. That's what I didn't catch that, but at least I'm glad I caught it where I could say it verbally. So we know, let's see, what do we got here? The magnitude of A at 1 squared. So we know A and 1 is 0, 6, and 12. That'll be 144 and 36. That'll be the square root of 180 squared. And then we know that AT, you have to find AT to use that formula. The first formula you don't, but you have to have AT to get AN using that formula. We have it right there, 6 square root of 3. But we had to get AT anyway because that's the question was asking for it. So you have 6 square root of 3 squared. So basically that's going to be 180 minus 108 square root of 72, which would simplify into 6 square root of 2. And that takes care of that one. Number 37, we want to find the unit tangent and normal vectors and unit normal vectors for the curve x equals t squared, y equals t at the point t equals 1. And I mentioned you may want to use a graph because the formula to find n of t, even for something that simple, can get kind of messy algebraically. Mainly because you got to find that t prime of t over the magnitude business. Anyway, I showed in the notes how to do this for 2 space. You'll see the best way to do two in the plane, 2 variables, and then I show coming up another problem how to do it in the best way to do it for space with the goal of trying to avoid using that formula. You can look at my notes and see how I did use that formula for, I think there's a problem in there, and you can see it gets a little messy. But anyway, so what we're going to do is we're going to find t of 1, the unit tangent vector at 1. So here's, that's your r of t is basically t squared comma t. So the derivative would be 2t and 1 right there. So it's 2t and 1. And then evaluate that at 1. It'll be 2, 1. And then the magnitude, because we have to make it a unit vector, r prime of 1 will just be the square root of 5, 4 plus 1. So your unit tangent vector at t equals 1 will be r prime of 1 divided by the magnitude of r prime of 1, and that gives you 2 over root 5, comma 1 over root 5. Now the idea on this, there's only 2 possible answers that the unit normal vector can be. You can get lots of vectors that are normal to it, but only 2 of them would have a length of 1. It's by keeping the same denominator and reversing the 2 numerators and changing one of their signs. So here, if I flip the 1 and the 2 like this, and then make the 1 negative. And the reason why is because the dot product will be 0. 2 times negative 1 plus 1 times 2. Don't worry about the 5 because it's 0 divided by square root of 5, still 0. So that would be 0. Or the other ways, reverse the 1 and the 2 again, but make the other number, in this case 2, make it negative, make it the opposite. Once again, that will dot to be 0. 2 times 1. 1 times negative 2, add those together, equals 0. So we've narrowed it down to 2 possible answers. Now, if you use the formula, which I don't recommend, and do the formula correctly, it will yield you directly to the correct answer. You don't have to go through this graph process that I'm doing right now. But I still would recommend it. Now, this one's pretty easy to plot. I wouldn't want this to be too complicated. It's going to be one of those 2. And the the normal vector is going to go inside the curvature, the concavity. So like this one's concave up, so the normal vector would go up on a graph that's concave down, like it is for this particular problem. Concave down, they'll have to go inside, with the concavity, not against the direction of the concavity. Now to plot that, it can be done in a calculator, but that's kind of a waste of your time, frankly, I think. So if t equals 1, I would just plot the graph for t equals 0 and t equals 1 and t equals 2. So if it's t squared and it's t, if you put in 0 for t, you'll get 0, 0, so it starts at the origin. You put in 1, you'll get 1, 1. And I put in 2, I'll get 2 squared 4, 2, which is that point right there. And then just kind of draw a little rough sketch. There's the curve. And the tangent vector is always going to go along, like tangent to the graph at that point. And the direction of that tangent vector does match the values for the x and y and the vector. In other words, the I and j, whatever to c. So that it's 2 over root 5, 1 over root 5. Don't worry about the root 5. Let's just look at the 2 and the 1, both being positive. So positive, when both components are positive, that means to the right and up. So right 2, up 1, divided by the square root of 5. So that's just illustrating that that's my tangent vectors going the right way there, the way it's supposed to. As your direction or orientation goes this way, you're going to expect the tangent curve just to be tangent to it right at that point. Now, the unit normal vector has to go inside that curvature, so it's got to be downward. Now let's go back and look at these two options I came up with here that has to be one of those two. I need to pick the one whose directions in the vector would match the direction that graph is going. So starting at that point, to get to the tail, the end of the vector, you're going to the right and down. So when you go to the right, that means the first component, the x component, is positive. Then when you go down, that means the y is negative. So I need to pick the answer from those two where x is positive, y is negative, and that would be this one right here. That's how I know that's the right answer. Because the x is positive 1 to the right, y is negative 2 down 2. It can't be that first one. It has to be this one. Therefore, that's the correct answer. Problem number 38. Now for 37, we showed how to get that unit normal vector for 2 space without having to use the normal vector equation. And I'm going to show you how to do it now for 3 space a little bit differently. The graphing method won't really apply for this in space. But the equation, which let's see, and I have it in the formulas right here. So what we're going to do, since the n is, and actually it's asking for all the components anyway, but even if it wasn't, if I only had to find like n of 1, I would still go find all this other stuff. Because there's 5 things here to find, 5 values. The n's the difficult part. So if you actually find the other 4 and then just algebraically solve for n, I promise you that's the best way to go. That's the best way to go. Because those other 4 aren't that bad to find. But that n is a mess. So let's go back to our problem. Let's see what we got. And all right, so there's our equation, or vector valued function, I should say. So we're going to get everything we need here. And r prime and r double prime, we need both of those. So those are pretty easy, 2t, 2, and 3t squared. And then the next derivative would be 2, 0, 6t. So they're giving us the value t equals 1. So a of 1 will be the second derivative at 1. Will be 2, 0, 6. Oh, it looks like I have the unit tangent vector done right here, but also have it done down. I'll wait till I get down the page a little bit here, so that's fine. I'll pretend like that's not there and then just look at this. So, oh, actually I see T1s. I use T1 here, but then I did it again right there, which is kind of weird, but yeah, so there it is. So the T1 would be r prime of 1 over the magnitude of r prime of 1, which is, yeah, so it's you put in 1, you get 2, 2, 3. The magnitude of that would be 4 plus 9, square root of 17. There's what the T1 actually is right there. It's just weird that I have it done that way. But anyway, so there's that result. So if you take AT, it's just A1 dotted with T1. That's easy enough. So you're dotting these two components together. So the square root of 17 can just sit there and just go 2 times 2 is 4, 6 times 3 is 18. So we get 22 over the square root of 17. Yeah, it's kind of bizarre. I have that written twice. Sorry about any confusion. So there's that. So you got two out of the 4 things down. You know, we need, well, and then we'll solve for the 5th one. There's 2 down. AN, I'm using the square root formula again. So the magnitude of A1 is square root of 40 divided by AT squared. We just got AT, so it's 22 over root 17 squared. And you'll get 40 minus 484 over 17. Common denominator for the 17 over 17. You'll end up with 196 over 17 under the square root. And the square root of 196 just happens to be 14. Okay, I've already explained this, the T1. We've already got that. And then now we have everything. So we have all 4 pieces. So everything's in pink that we need here. All 4 of those are in pink. And then we can just solve this algebraically for N1. So the A1 on the left side, 206, equals the AT, which is 22 over root 17, times T1, right here, plus AN, which is 14 over square root of 17, times N1. N1 is our unknown variable that we're solving for. So just got to do a little algebra here. It's not too bad. So what I did here is kind of did 2 steps at once. It's not too complicated steps. But I distributed the 22 square root of 17 through that vector and then just moved it over to the other side. So there's the minus. So distributed, moved over and made it minus. So we subtract. Oh, that's a mistake right there. That should be not a square root underneath there. I'll fix that in the original solutions file. But I'll keep going for now. That's just 66 over 17. And then common denominator, so you just make all those over 17, subtract them, you'll get this vector. And then to solve for N1, you just multiply by the reciprocal of that coefficient. And then so it's square root of 17 over 14, so just distributed right through there. And I just kind of combine the radicals and left the square root of 17 on bottom. Maybe I should have rationalized it and put it back on top. That's all right. I mean, there's a bunch of different ways you could write this answer, but maybe that was bad form there. Maybe I should have just left the square root of 17 on top. And anyway, that's okay. If the key is it's correct, except for that one little typo right there, which I'll fix. All right, and then there's your N1 vector. So it needs to be a unit vector. And another important thing, if you wanted to check, I'm just saying, when you take N1, if you dot it with T1, you better get 0 because N1 and T1 are, perpendicular to each other. So that better be 0. I've checked it before. It definitely is. Okay, arc length. You can use the numerical features of your graphing calculator to take care of this, but you just got to get it set up properly. And the arc length formula is right there. It's just the integral from a to b of the magnitude of r prime. So don't forget the chain rule. The derivative of cosine of 3t is negative 3 sine of 3t. The derivative of sine of 3t will be 3 cos 3t, all because of the chain rule. And z will just be, derivative will be 4. So you put this under a radical. You have negative 3 sine of 3t squared plus 3 cos of 3t squared plus 4 squared, which you could kind of integrate, but actually there's a little trick to this one that works out, makes this problem actually very, very easy. Even if you were integrating it manually, it's very, very simple. But, you might want to expect to see one on a test, but you can use the calculator, but if not, it might be like a U substitution. It's not going to be too complicated, but, it might be just a basic U. Don't assume it'll be this easy, in other words. Might be a U sub. And let's see. But anyway, the catch on this one is you have 9 sine squared of 3t plus 9 cos squared of 3t. Well, so they're, sine squared of something plus cos squared of the same something equals 1. So actually then that just all turns into 9. And for the first two added together is 9, and then plus 4 squared, and so it'll be 9 plus 16 will be 25. And then so you have square root of 25, which is just 5. So the antiderivative of 5 dt is just 5t. And then put in pi over 2, put in 0, subtract, and you get 5 pi over 2. Like I said, it might not be quite that easy on a test problem, but you can just numerically integrate. And number 40. Let's see, find the curvature. Now, I don't have the other curvature formulas. In fact, I think in my formula sheet I only put that one because I don't even use the other two. But anyway, using the curvature formula that I like, it's got to be considered a space vector. You might be able to do this with those other formulas. I don't know them off the top of my head. Maybe not. I don't know. But that's no problem. So even though because that formula has a cross product, and the idea of cross product only applies to space vectors. But that's no trouble. If you have an x and a y, all you have to do is just add a 0 for z, and then you've turned it from a plane to a space. So it just needs to just added a 0 in there for my cross product. So there's the r. So I'll just put the 0 in there. R prime will be 2, 2t plus 2, and 0. So r prime of 0 will just be 2, 2, 0. And then the next derivative will be 0, 2, 0. The magnitude at 0 will just be 0, 2, 0. There's nothing, since it's constant, nothing to plug in there. Do the cross product. You'll get 0, 0, 4. Take the magnitude of that, you'll get 4. So it's the magnitude of the cross product divided by the r prime at 0, magnitude of that cubed. So here's r prime, 2, 2, 0, which the magnitude would be 2 square root of 2 cubed. It'll be 16 square root of 2. And then so it's 4 divided by 16 square root of 2, which is 1 over 4 square root of 2, which of course, you could rationalize. If you did rationalize it, square root of 2 over square root of 2, you would actually get square root of 2 over 8 as the answer. So, all right, that takes care of problem number 40.